Hey, so I believe that last lecture we got up to as far as working with weak acids and calculating the pH of weak acids. And I believe I got as far as covering that if you have, for instance, a weak acid, and we'll just call the weak acid, just be any acid, any weak acid, and we're just going to call it A, just to represent that it can be any weak acid. And as an acid, it is going to be a proton donor. So we'll call it H, with the H representing the hydrogen, or proton, which is capable of donating. And on the other side of the equation, if you were to take this weak acid and you were to drop it into some aqueous solution, into water, what you'd have released is that it would dissociate. That is, that the acid would release its proton because it's an acid. It wants to. It's in a condition where it would like to donate a proton, or it's comfortable to donate a proton, and so it's going to donate that proton as H plus. So, for instance, what would happen is that in the bond between H and A, the A would take the electrons off the bond, and so the hydrogen would be left without them, and so the hydrogen effectively is a 1+ charge, so it's just H plus, aqueous again, plus the acid now, because it has has that extra electron, it's got a negative charge to it now, so it'll be plus I should draw these charges outside actually. Better. There we go. So we're going to have these two have been generated by the weak acid, or just in general actually, just any acid in solution is going to, because it's an acid, it's going to release the proton. It's a proton donor into solution. There's the proton. And now, because it's gained, taking that electron from the hydrogen from the bonds that was between them, it's now got a negative charge to itself. These are ions now in solution. If it was a strong acid, this would happen 100%. So we would just draw an arrow, and I'm just going to put a 100% just above it, just to make my point. But if we're talking about the weak acids, instead, it's something that's not going to dissociate completely. In fact, it's going to be an equilibrium. And equilibrium does not mean that there are equal amounts of them. It doesn't mean that, for instance, there's 0.5 molar on this side and 0.5 molar on this side. Those amounts are actually going to be typically different. In equilibrium means that they are balanced, in that they've reached an equilibration point, a balance point, where they're no longer moving. There's no longer any transition. They're constantly transitioning back and forth, but they're no longer going up and down. The concentrations that it's at is at a set level. It's just at a set. The overall concentration is no longer wavering up and down. It's at a set level that it's happy to be balanced at. Kind of like if you have a seesaw and you've got the balance in the middle, and if the balance is exactly in the middle, then this is going to be perfectly, if you have one force on one side, one force on the other side, and they're equal forces, and the fulcrum, the balance is in the middle, then this is going to be balanced. But if, for instance, I moved the fulcrum of the balance and I moved it more over this side, well, in order for it to reach a balance, you'd have to have more force pushing down on this side. You have to have a greater weight on this side. But they're still balanced, but you just have more on this side than you do on this side because of the position of the fulcrum. But they're at a balance. It's not going up or down. It's not changing. It's just at an equilibration where it's happy to just sit at that point. And so typically what I was saying is that it's not balanced, it's going to be equal on each side. It's balanced as in that there's no pressure for something to move over from one side to the other. It's happy with the status quo, you could say. The system is happy with that status quo, and so it's just going to stay like that. So typically what you might see instead actually is perhaps these are 5.5 molar on both sides. I've had them previously, how I wrote them. But if the balance is such that there's more product, then it might be, say, 0.1 and 0.9. Doesn't have to add up to 10. You know, let's just this to get rid of that. Say 0.7. So this is where the equilibrium favors making product, and it's balanced now, and it's not going. It may kind of go backwards and forwards, and be reversible, but it's going to balance out at being 0.1 molar of reactants and 0.7 molar of products, and it doesn't want to push over and make any more reactant or make any more product. They may be going backwards and forwards, but the sum total is always going to be 0.1 molar of reactants, 0.7 molar of products. That's just the way that it's balanced out. Whereas conversely, it could be that the equilibrium favors reactants. You don't get very much product at all. And so instead, let's say it's 0.6 molar of reactants and 0.2 molar of products, something like that. And the way that you can tell which way the reaction is going, whether or not the reaction favors making products or the reaction favors making the reactant, is dictated by the constant that goes above the equilibrium, which is always K. Doesn't matter whether or not we're talking about acids, doesn't matter whether or not we're talking about any kind of chemical reaction. We always have a constant capital letter K. There's a little letter K that's rate, but we're not doing that. We're doing equilibrium constants. It'll typically be something like KEQ. But as we cut, and that's the case where, for instance, when I was doing the example last time with water. But when we're talking about weak acids, we call it Ka. And it's just a way of communicating from scientist to scientist. Hey, we're talking about Ka, so that must mean that we're talking about dissociation of weak acid. But ultimately, at the end, it's just K, just the constant, just an extra label that's given to it. And if you think about it, pull this back up again. If we want to know whether or not the equation favors making product or favors making reactant, we can express this with a ratio, right? You can a ratio of product to reactant tells you how far over it is. So we do, for instance, P divided by R, and that will tell you what the ratio of making product is. Because if the product is a big number and the reactant is a small number, well, that means that you've got a big number divided by a small number, which means that you're going to have a, let's say, it's a big number divided by a small number. That means that the result is going to be a big number, which means that that's communicating that we're favoring making product. Whereas conversely, if you don't get very much product and you have a small number for the concentration of product, you have a high number for the concentration of reactant because you're not making not very much reactants turning into product. Well, then you've got a small number divided by a big number, which is going to give you an even smaller number. And so that's communicating that you don't have very much. That's a way of communicating that we don't have very much product and we mostly have reactants, and the reaction is proceeding very far over to the right. So big Ka tells us that the reaction is going over, or just big K in general, but we're talking about the weak acid. So a big Ka means that the weak acid is associated more, and a small Ka means that the weak acid is dissociating less. To the extent actually where if the number is greater than 1, then it means that that's what I mean by small number. A number greater than 1 is going to mean that you've got more product, and the number smaller than 1 is going to mean that you've got more reactants. And so this is reflected by the equation products, or even more basic, that in general it's the equation is concentration of product divided by concentration of reactant gives you K. And we're talking about weak acids, so it's Ka. And the product is H plus and A minus. Our reactant is HA. And so that's the equation that we have. And when we are working with, I said that there are several equations that you guys need to remember. There's the first equation, which is for working with strong acids, where if you take the negative log of the concentration of the strong acid, that will tell you it's pH because it dissociates completely. Because whatever the concentration that you have to start with, whatever the concentration that you have to start with, because it dissociates, and to start with, you've got no ions, but then because it dissociates completely, you're going to have no starting after diluting and adding to water, you're going to have no of your strong acids dissociated completely. It's just that arrow, but whatever the concentration you started with, it's also going to be the concentration of the products that you have. And then pH is just the negative log of the hydrogen ion concentration. And we know that to be the same as the starting concentration of your strong acid. So you could just put that in there. And boom, negative log of 0.1 is 1. Easy. So that's where it's with strong acids. With weak acids, we use this equilibrium equation, and the Ka will be given to you, the Ha will be given to you. You just need to figure out what the concentration of hydrogen ions is. So you just rearrange the equation. So you can just bring that over there. So let's just go Ka multiplied by Ha equals H plus A minus. And I've given you this number, I've given you this number. These numbers are always going to be the same, because something splits. It splits exactly in half. And so although, it splits exactly, if I've got one thing and I split it exactly in half, I've got one thing and it splits into 1 and 1. I have one of these each. Their size is smaller relative to this one, but the number of them that I have, I still have, I've got one of these, and I've got one of the left half, one of the right half. Whereas if I had 2 of these, well, I can have 2 of the left half and 2 of the right half. So these are split into equal halves. So if I have, I want to solve for hydrogen ion concentration, and so that will give that the figure X. And I know that the A minus is going to be the other half, so that's also going to be X. So it's X multiplied by X, so it's X squared. So I know this number, I know this number. Let's just say I've already figured them out. Or let's just say it's 1 times 10 to the negative 9 multiplied by 0.1, which is 1 times 10 to the negative 8 equals X squared. There. Let's just square root both of them. That'll give us X. And then if I just take the X is therefore the hydrogen ion concentration, but we don't want to just know the hydrogen ion concentration. We want to know the pH. I mentioned why before, but pH is it's just we want to know the hydrogen ion concentration because it can interact with a lot of molecules, and it's important in chemical reactions. And so we want to know that. It's very important biologically, so we might want to know what the hydrogen ion concentration is. But it's going to be a weird number that's it's going to be a weird number on a very large scale, and we don't want to work with that. So we just take the negative log, just transform it to make it an easier number to work with. So we found out what the hydrogen ion concentration is. To find the pH, we're just going to do the negative log of that, because P is just mathematician shorthand for the word negative log, or the term negative log. So we could say, I could say to you, hey guys, what's negative log H plus? And instead I just say, what's pH? Because negative log and P mean the same thing mathematically. It's just a shortcut. So that will give us the pH. Now, the next thing I want to, and I think I covered that in the last lecture. I did that a couple of weeks ago, so I can't remember. I'm pretty sure I covered this in the last lecture on water. But what happens next for the third and final equation? Remember, the first one is strong acids. The second one is I just gave you, where you take this and you rearrange it. So you just want to write this and in your top of your paper and just rearrange it. Sulfur X squared, then sulfur X, then take the negative log off that. The next thing to do is the third equation, and this is where we're talking about buffers. Now, to illustrate why, I'm going to erase all of this. I'm going to draw a graph. So for this graph, let's go along the y-axis here. This is pH, and along the x-axis, along the bottom, we're going to have added base. Okay, or let's just like, I'm just going to call it OH minus. Okay, so think of what pH is. Okay, pH is the negative log of H, which means that the negative log of hydrogen ion concentration. So the hydrogen ion concentration is going to be a number such as 1 times 10 to the negative 7, 1 times 10 to the negative 6, 1 times 10 to the negative 5. Let's go one more. You know, I'm going to go one more. Okay. So what do you see here about this number? This number, as we move down, this number is actually getting bigger, isn't it? As we go down here, this is actually reflecting that the hydrogen ion concentration is increasing because you're getting, you're getting fewer. This has got 7 decimal points, or 7 zeros after the decimal point, 6, 5, 4, 3. Yeah, so it's actually getting to reflecting a higher concentration of hydrogen ions as we move down here. What is the negative log of these? Well, you just take the log. You just take the index or the power here. And since it's negative log, you just reverse whatever the polarity is. So instead of it being negative 7, it's going to be 7. So the negative log of these is 7, 6, 5, 4, 3. And so you can see actually that as if we start here at 5, so if the hydrogen ion concentration is 1 times 10 to the negative 5, if I increase the concentration, I add some more hydrogen ions by going down, see that the pH number goes down. Even though the pH goes down, even though the hydrogen ions are going up, because it's taking the negative log, it's reversed, it's the other way around. Whereas if I decrease the hydrogen ions, then the concentration of hydrogen ions, the pH goes, I decrease the hydrogen ions present, then the pH goes up, I go up, and the pH goes up. It's just because of the way that negative log transforms things. It's reflecting that you're starting from a very, very small number, and you're going down to a slightly less small number. And because you're doing the negative log, you're reversing the polarity, you're reversing the sign. So it gets a little bit confusing that you're working against each other. But if you have a pH, when you go down in pH, it's saying you've got more hydrogen ions. It's a lower pH. If you have a higher pH, then it means you got less hydrogen ions. So what does that mean in solution? We've got a chemical reaction, an acid-base chemical reaction. And remember, I'm showing here pH and added base. I'm showing on the x-axis concentration of it. We've got the reaction. Let's say that we've got some hydrogen ions in solution. They're not going to be sitting around like this, but I just do it like this. And if I add in some base, that OH minus, well, I'm generating water. Okay, and so this here, I may have, let's say, 1 × 10⁻⁷ hydrogen ions, and let's say that I have 1 × 10⁻, I react that 1 × 10⁻⁷ ions of base. This is P4. And we've got 0 water because we haven't made it yet. But afterwards, they react together. I now have 1 × 10⁻⁷ water. Because you figure this is the 2 halves that come together to make a single one unit again. But how much base do I have? Well, it's all reacted, so I've got none. How many hydrogen ions do I have? It's all reacted, so I've got none. So when I react acid with base, I remove the hydrogen ions. There's a lower concentration of hydrogen ions. And remember, when I remove the hydrogen ions, the pH goes up. So let's start here with this. So this is just added. I'm starting out with a weak acid, and let's say that and I'm adding some base to that weak acid. This is just arbitrary amounts of base. This isn't real. This is just a thought experiment. Okay, and I'm just adding like drops of base. Okay, let's just keep it just very, very simple, very basic. I'm just adding a bunch of base, drop by drop by drop. Now at the beginning, I haven't added any base yet. And so we've just got weak acid in solution. And the pH, let's say, is about pH 2. Down here. This is just, I'm just making it up in order to illustrate the point. Now, what happens is that as I add the base, I add it, the pH is going to go up, right? Because of that reaction I'm showing up here. I wish I kept it on the board now. The reaction I'm showing up here, where I'm so I'm reacting the hydrogen ions with base, and so I'm removing the hydrogen ions as I add base. So, and as I'm removing hydrogen ions, the pH is going up to reflect that there's a lower concentration of hydrogen ions. And actually, at the beginning, what happens is that it tends to go actually very, very quickly. See, it's much steeper. It'll level out, level out, level out. So it reaches this point here where adding base is no longer increasing the pH quite so much. The pH, even though I'm adding more base, pH, notice the pH isn't changing anymore. Now it happens again continually. So I reach a point where it overwhelms and it goes up, and goes up rapidly again. This point here, at this point here, it's being buffered. That is what a buffer is. A buffer is when a weak acid is able to soak up. I'm using very kind of informal terms here, but just to communicate the point, a buffer is when a weak acid is able to soak up the hydroxide ions or the base that is being a base is just a proton acceptor, but in this and often it's a hydroxide ion. It's the weak acid is able to soak up the base so that it no longer impacts the pH. It's no longer causing the pH to go up. It's kind of it's buffered. This is a buffer region, and this region here is where it has been buffered. Now, the very center of this region here, right there, we were to go across this point here. This is pKa. That point there is the pKa of the weak acid. Now, think about what pKa might be. Remember what I told you about what P is? P, I'm going to put needs instead of equals, just to try and communicate that it's, you know, it's more of a language term, if anything, really, than I mean, it's using language to describe a mathematical term. But P means negative log. It's just a mathematician's shorthand. It just means that mathematicians before the age of the calculator and the computer, rather than writing negative log again and again and again, they would just write P. It just means that that's all it means. So we've got a P here, and then we've got the Ka. Remember what the Ka was? The Ka was for the equilibrium. The Ka was the we can describe the Ka, remember, as being products divided by reactants. Just want to make sure you guys can actually definitely see. So it's products divided by reactants. It's going to give you the Ka. And that is going to, it's telling you how far over, whether or not you've got more products, more reactants, telling you how far over the equilibrium is, and that kind of balance. Okay, so it's telling you how much the weak acid is dissociating. That's what Ka is. And so the pKa is just the negative log of the Ka. And why do we do that? Well, when we had pH, what have we done? We've taken the negative log, and so the H plus, the concentration of H plus, it's just on this really large scale. Say for from 1 times 10 to the negative 14 up to for instance 1, and here was just a really long range. That's really big. By taking the pH, instead of it being, that's a huge range. That's 14 times. You can multiply by 10 14 times, and before you reach from one end of the scale to the other end of the scale, multiply this number 10 times to get to the end of the scale. That's multiplying a lot of time. That's multiplying by a lot. pH, how many times can you multiply from 1 to get from 1 to 14? How many times can you multiply by 10? 1.4 times. So it's a much smaller scale. That's not an H. That's where I've drawn like a. That's just a much smaller scale. And so what we're doing we transformed the hydrogen ion concentration and put it onto a different scale. Well, if you think about it, it's only fair that we judge the Ka by the same metric. And so by putting it onto, by finding the pKa, we're just putting it onto the same scale so that they're now comparable. They're now in the same group. So at the buffering point, the very center of the buffering point is equal to the pKa of the weak acid. And the point at which a weak acid can buffer a solution, it's weak acid works best at buffering a solution between pHs that are +1 or -1 of the pKa. That's for the best buffering capacity. That's this box here where it's actually capable. It's not buffering here. It's not buffering here. It's only capable of doing it about +1 pH unit of pKa. And another fact that I'm put with you as well is if you think of let's think about the reaction that's actually going on here. So what we have is that we have HA plus, let's call it sodium hydroxide, NaOH. So there's our base, which is adding the ions. Have I got space? Yeah, I've got space. The chemical reactions happening is that you've got this acid plus base, and they're reacting to give you the hydrogen ions. We're ignore the water for now, but let's give it as they're reacting. No, let's not do that. Do it like that. So actually, we give it water plus salt. Sorry, which is going to be the salt is going to be so we've got the H2O. So there's the H2, H1, H2O. So there's our H2O. We're left with Na and which will be like Na plus and A minus. They're going to come together as if you have two ions come together. That's known as salt. So let's call that Na. And I'm just going to put the little plus and A minus. Those charges aren't actually there because they're cancelling out. Or just putting them there just so that as like a visual tool of remembering where everything came from. It's actually, it would be like sodium benzoate or something, sodium acid. That's the way that it works. So what you have is that your water and salt. So acid plus base gives you water and salt. And so what you're having here is that you are you're producing there's a whole mixture of reactions going on here. You've got, first of all, you got your HA, and it's dissociating into H plus and A minus. And then you've also got the chemical reaction with the base that's going on, because you haven't, you're only adding a small amount of base at first. So at the beginning, there's a lot of acid, not very much base. So you have more of this bottom reaction where you have the more hydrogen ions, you can see. But as we add in more base, you kind of start switching more towards this reaction. So we've got a whole bunch of kind of reactions going on. We've got a mixture of our starting acid. We've got our hydrogen ions, and we've got our salt, which is reflected here. So this is our we've got a whole bunch of things in solution. We've got our acid, which is releasing, some of it is releasing hydrogen ions. Some of it is reacting with the base. We've got a whole bunch of different kind of reactions going on here. And all of these reactions are contributing in some way in the pH. We want to be able to link them together. We want to link together the unreacted material, the reacted salt that's produced, the hydrogen ions that are produced. And at this, we do that with an equation, which I'll show in a moment. But what I want to reflect here is at this point, pKa, that's in the very center. This is at a point where the concentration of HA and A minus salt is they are equal. So at this point here, this center point here at pK at when pH equals pKa, HA equals A minus. So the weak acid is 50% dissociated at this center point. When pH equals pKa, HA and A minus are equal. Okay, so in this whole big bunch of reactions here, these two different reactions that are occurring, at the point where we've added enough base to raise the pH of the solution, so the pH is equal to pKa, the concentration of HA and the concentration of the salt that it makes, HA, and the salts that it makes, those are concentrations are balanced 50-50. The acid is 50%, I guess, in a way it's 50% used up where you reach pKa. And pKa doesn't have to be pH 7 neutral. pKa could be 3, or pKa could be 12. And sometimes it is. And if pKa was 7, then it would be good at buffering between pH 6 and 8. And pH 3, it would be good at buffering at between pH 1 and 4. At pKa equals 12, then the weak acid would be good at buffering at between pH 11 and 13. And at that point, those respective points, if you added enough base to reach where the pH equals pKa, at that point, then the weak acid is, I guess if it's the pKa is pH 12, it won't be a weak acid, it'll be a weak base instead, but the concept is the same. You add enough of the base to these weak acids to raise the pH to where pH is equal to pKa, and that's when the acid's like half used up, it's half reacted, and there's a 50-50 mixture of acid and salt. So how does this tie in with that final equation? We're almost done. How does this tie in with that final equation? So think about this curve here. Think about this curve here, these 2 points. They're 2 logarithmic, exponential, that's the word I was looking for. They're 2 exponential curves. See, this goes exponential and this goes exponential. They're 2 different exponential. This is a positive exponential, this is a negative exponential curve. They're both exponential curves. And how do we reflect these? How the exponential curves look mathematically in terms of a formula? That's where we use log. And you see log's coming up again. Now, that means somewhere in the equation that describes this graph, there's going to be a logarithm on its own. So let's find that logarithm. It's probably going to have something to do with the logarithm and the concentration of the base added, and so you can get kind of try and see that if you were to take if there was some kind of logarithm of the number of the concentration of the base added, that's going to affect the graph in an exponential curve kind of way. And so let's see what that equation is. So let's go to our equation of H plus A minus over HA equals Ka. Now that's the equation. That's the equation number 2. Remember. So what do we want? So we want to have the negative log of. We want to ultimately know the negative log of H plus. And then as well, let's take the negative log on this side as well. And so if we end up taking and then if we take the log, the negative log of everything here, we rearrange that equation. Okay, so we get take equation 2. We just rearrange the equation, take the negative log of both sides. I'm not going to go through the math of how that occurs, but what we end up with instead is, see, we're taking the negative log of H plus, so we end up with pH, taking the negative log of Ka, so we're going to have pKa, and then we're going to do plus the log of A plus the log of concentration of A divided by the concentration of HA. Okay? That's where we've just taken we've just rearranged this equation, we've just done some maths on this equation. We've come out with this in the end. This is that Henderson-Hasselbalch equation. That's equation number 3. This is the third equation you've got to memorize. pH equals pKa plus log of the concentration of the salt divided by the concentration of the weak acid that you have left. And so there it is. There's that log. There's that log which is causing that curve. And let's just demonstrate why. So how much room do we have on the other side of the board? Not very much. The camera is pointed over here. So what I will do is I'll just move it to make some room. So here's the Hasselbalch up here at the top. I'm not bothering drawing in the square brackets, just being quick. So, so let's start first of all. Remember that statement where I said at this middle point is where pH equals pKa, and the A minus the salt and the weak acid that's left over that hasn't dissociated left yet, they're at a 50-50 point. Well, if you think about it, if these are at a remember I said that when pH equals pKa, HA equals A minus. It's 50-50. You know, it's 50% dissociated. You've got an equal concentration of weak acid and the salt that's being produced by the reaction with base. So let's see why that is. So if it's let's just stick with the numbers 50-50, right? If it's 50-50, then here we go. pH equals pKa plus log A minus over HA. Let's substitute in the numbers. pH equals pKa plus log 50 over 50. Well, what's 50 divided by 50? 50 divided by 50 is 1. And what's the log of 1? The log of 1 is 0. And so pH equals pKa plus 0. So pH equals pKa. That is why pH, when pH is equal to pKa, you know that A minus and H plus are the same. The amount of salt that's been produced in the weak acid it's the same. And then let's look at it then in terms of this curve. Now, if you think about it, at the beginning, so pH remember is the y axis equals pK plus log. Okay, now let's say that you're right at the beginning and you have, let's do some nice easy numbers. You're right at the beginning, you haven't added much base yet. So the concentration of HA is, say, 100. You haven't produced very much base yet. So this number at the top, A minus, so you haven't produced much salt yet because you haven't added much base. So this here is going to end up being a very small number, okay? This is going to be a small number. But as I keep adding base, this number is going to grow. And let's say, you know, it grows and becomes 25, 75, and then it becomes 40, 60. Okay, then that number started out as a very, very small number. You know, it's so 1 divided by 100 is going to be 0.01, and then let's say we change it to 10 divided by 100. Let's just do it. Let's just make these numbers nice and easy. Well, that's going to be 0.1, and then what we have now, we can see that if we take the log of these numbers, what you're doing is that you're adding it to the pKa, and this is because it's a factor of 10. That's going to, and when we add it onto the graph, it's going to make a quite large. This is where we started out, and then it's going to make, because we're taking the logarithm of these numbers, where it's going to make an exponential addition to pKa. It's going to be very rapid up until you get to the point where eventually it's 1 and 1, and it's 1, and so you're going to have a log of 1, and it's going to be log of 1 is equal to 0, and so pH pKa where you've reached this point. So the reason is because as you have the top number divided by the bottom number, and the fraction that's produced, you take the log of that fraction, it causes it to multiply up fast at first, and then slowly, and then as you then switches around, and you're now adding so much base that you've gone over the 50-50 mark, and you instead now have a larger number on the top. So 100 divided by 10 equals 10. So a larger number on the top, and then say 100 divided by 1 equals 100. So you get a large number by the top, and as this number gets larger and larger, because the ratio is going more and more, you're taking the log of that, and it's making it accelerate and curve and go up faster and faster. And that's why the Henderson-Hasselbalch equation is just the points on this curve. And all you have to do for my questions in the exam, I'd like you to generally understand this concept that I'm describing, and there'll probably be 1 or 2 small questions in the exam which address this concept which I'm describing. And it's important that you understand this concept. But there's only 3 equations that you need to know for the math part of my exam that makes up about 50% of the points available for about 50% of the points available for the water and pH section of my exam. About 50% of the points available are just for remembering, being able to do these 3 equations. Number 1, with a strong acid, the concentration of H plus is equal to the concentration of the acid, because it 100% dissociates. So I guess in a roundabout way, I have an equilibrium constant. It's just really, 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 really big. So it's effectively 100%. And so because HA is equal to, because H plus is equal to HA, you just need to take the negative log of HA, which is effectively the same as the negative log of the of HA. So I think I misspoke. So we want to know the negative log of H plus to give us pH. But effectively, because H plus and HA are the same, just take the negative log of HA, and that will give us the pH. Now, don't forget, this needs to be in molar, not millimolar. not micromolar, but molar. It's always in molar. So if I say to you 250 millimolar, that is equal to 0.25 molar. All of these are a factor of 1,000. Molar to millimolar to micromolar, they're all a factor of 1,000. So I will probably give it to you as a millimolar. So just remember, but I might not, but I may do. So just remember to convert it to molar. Always needs to be molar. That's the first equation. The second one is going to be with the weak acid, and I will tell you when it's a strong acid or a weak acid. But classic strong acids are going to be hydrochloric acid, HNO3, which is nitric acid, or sulfuric acid, H2SO4. These are classic strong acids. H2SO4 is a little bit more complicated. It's got two hydrogens that it can donate. So it's got two pKa's. It can donate it twice, or no, it doesn't have two pKa's. That's a lie. That'd be if it was a weak acid that had two protons. But it's not. It's a strong acid, which means it doesn't have a Ka or a pKa, or it does, but it's insanely large, and we just ignore it. Just put 100%. But the point is that if I was to use the example of H2SO4, because there's two hydrogens that be given away, and it gives away twice as many. If the concentration of H2SO4 is 0.1 molar, because it gives away two hydrogens, the concentration of hydrogens is going to be 0.2 molar, because it gives away two. It's got two. And this is actually referred to often as a thing called normality instead, where what you do is that we don't really use this very often. It's more of like an old chemist thing, but 0.1 molar H2SO4 is 0.2 normal H2SO4. And what you do is that you just multiply the molarity by the number of hydrogens that can be donated in order to get the number of normals. And so, for instance, HCl, 0.1 molar HCl is going to be 0.1 normal HCl, but 0.3 molar H2SO4 is going to be 0.6 normal H2SO4. It's just reflecting that. Anyway. For the weak acid, number two, the weak acid, we have that equation H plus OH minus, no it's not, A minus divided by HA equals Ka. And we know that these are going to be the same. So we rearrange the equation to be concentration, remember, in molar. Concentration of the weak acid multiplied by the Ka is equal to x squared, because these are both x. Step one, A. Step B is to take the square root of both sides. Step C, take the negative log of x. Now you solve for x. That gives you the pH. So that is the second equation. Then the third equation. Keep this up there. In molar. third equation, that Henderson-Hasselbalch equation, pH equals pKa plus log A negative over HA concentrations. And you just need to rearrange this equation. I will give you, I'll give you a lot of the numbers that need to go in here. I will always give you the Ka. But of course, if I give you the Ka, I ask you to do a Henderson-Hasselbalch equation, you'll have to remember do the negative log of it to get the pKa. I will ask you guys for the pH. I will say, probably be a follow-on question. So I'll say, this is the weak, what's the pH of this weak acid with this concentration and this Ka value. And then you'll solve for X and then take the negative log of X. And then I'll say, then you add in some base. And so you'll then have to take the negative log of the Ka, feed it into here. And then you have to feed in these two numbers here in order to determine the new pH. Remember, acid plus base equals makes salt plus water. Think about what you started with. Think about what you end with, okay? So remember, I'm going to be telling you part A of the question, say 0.01 molar acid. That's what we started with. And then say, well, to this was added 0.005 moles of base. So that's what we're gonna, that's the reaction to taking part. And you haven't made anything yet. So 0. What are you going to end up with after that? Well, the limiting factor in this reaction is the amount of base. So that's so you can only make as much product as you have base. So product is salt. So you're going to have 0.005 moles of the salt. We won't worry about the water. I'm just going to scrub it out. We're not interested in water. Water doesn't feature in that equation, so we don't care. Not important. How much base do we have? We have 0. So we've used it up. How much acid do we have? Well, we've used some of it up again. Because it's reacted with the base, isn't there? So there's not as much as there used to be. So what is it going to be? 0.01 minus 0.005 equals 0.005 moles. And now I can feed that acid, feed that salt, feed that into the equation. And then we have it. We have the pKa from the Ka from earlier, have the A minus, have the HA, just need to solve for it. Divide A by HA, take the log of it, add it to the pKa, and that will give us the pH. And what you might notice about this one, what is, you can actually figure out, just from what the numbers I've given here, you don't even need a calculator right now. You know from this what the pH is. You know without a calculator what the pH is here. And think about it for a moment. Think about the numbers that we're substituting in. 0.005 into the bottom, 0.005 into the top. They're equal, aren't they? So it's going to be equal number divided by equal number. It's going to give you 1. Log of 1 is 0, which means you're adding 0. So pH equals pKa. We're at that point, that 50-50 on the graph. That midpoint. But pH equals pKa. The concentration of acid, unreacted acid, and salt is 50-50 is equal. And so that is everything to solve here. Just remember the key points in molar, equation 1, equation 2, equation 3. And don't forget, when we react them together, we've got to do this little thing here to reflect that some of it has been used up. We've got to reflect that the reactions occurred. If I wanted to be kind of tough, I might say, for instance, remember it's in molar. I might say, for instance, 10 grams of benzoic acid, I'll just call it BZH, was dissolved in 1 liter of water, and that the molecular weight of benzoic acid it's 66. I think it's 66. 66 grams per mole is the molecular weight. And so I remember this needs to be a molar. I haven't given you a molar. I would have given you the grams of the acid, the amount of solution, and the molecular weight of the molecular weight of the solid. No, I reckon it's 76. I'm just doing the math in my head. Anyway, so what you'd have to derive the molarity in order to solve this, and for that you would use the equation number of moles equals mass over molar mass, and so our mass is 10 grams, and our molar mass is 76 grams per mole. That'll give us number of moles, N, which is mole, not molarity. Molarity is something different. Molarity is molarity, or I always do it as molarity is a concentration, and just measured in molar, but number of moles is a number of moles. So concentration equals the number of moles in however much volume. Well, it's in always in liters, so it's 1 liter. So it would just be concentration in molar equal to the number of moles divided by the volume in liters. So it should be N divided by 1 in this case, would give us the concentration in molar. And then we'd have that molar, it'll feed it into this here. But I'm not going to do that. But I would like you guys to know how it's done, because I think that's kind of important. But that's everything that I wanted to talk to you about today. I'll give another lecture real soon where I'll talk about the intermolecular forces and water, and that will cover everything for the water lectures. Thank you very much for your time and attention.